Let yourself settle in comfortably as we embark on a journey through our cosmic home, a vast island of stars floating in the infinite ocean of space. Close your eyes and breathe deeply as we explore the Milky Way, the galaxy that cradles our solar system and everything we've ever known. Look up on a clear, dark night, far from city lights, and you'll see a luminous band stretching across the sky, like a river of milk spilled across the heavens. This is how our galaxy appears from our vantage point here on Earth, and it's how it earned its name. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, while the Romans named it Via Lactea, the Road of Milk. But this glowing band is just a fraction of what's really there, a cross-section of something far more magnificent. The Milky Way is a barred spiral galaxy, one of billions of galaxies scattered throughout the observable universe. Imagine it from above, and you would see a magnificent pinwheel shape with graceful spiral arms curving outward from a bright central bar. Our galaxy spans approximately 100,000 light-years from edge to edge, though recent observations suggest it may be even larger. To put this in perspective, a single light-year is the distance light travels in 1 year, moving at 186,000 miles per second, covering about 5.88 trillion miles. So our galaxy stretches across roughly 600,000 trillion miles of space, a distance so vast it defies human comprehension. Within this enormous cosmic structure, the Milky Way contains an estimated 100 to 400 billion stars, though the exact number remains uncertain because much of our galaxy is hidden from view by vast clouds of gas and dust. Each of these stars is a sun, many with their own families of planets, moons, and perhaps even life. Our own sun is just one ordinary star among this multitude, located about 26,000 light-years from the galactic center, roughly halfway out along one of the spiral arms called the Orion Arm, or sometimes the Orion Spur. Breathe slowly now, and let yourself drift through this vast expanse. The Milky Way is not standing still. It's rotating, spinning like a cosmic carousel. Our entire solar system orbits the galactic center at a speed of approximately 515,000 miles per hour. And yet, despite this incredible velocity, it takes about 225 to 250 million years to complete just one orbit around the galaxy. Scientists call this period a cosmic year, or galactic year. Since the Sun formed about 4.6 billion years ago, it has completed only about 20 orbits around the Milky Way. The last time our solar system was in its current position in the galaxy, dinosaurs had not yet appeared on Earth. At the very heart of our galaxy lies something both fascinating and mysterious, a supermassive black hole called Sagittarius A*, pronounced Sagittarius A star. This cosmic giant has a mass equivalent to approximately 4 million times that of our Sun, all compressed into a region smaller than the orbit of Mercury. Despite its enormous mass, Sagittarius A* is relatively quiet for a supermassive black hole, not actively consuming vast amounts of matter like some of its more violent cousins in other galaxies. Scientists only confirmed its existence definitively in recent decades, and in 2022, astronomers released the first direct image of this black hole, showing the glowing ring of hot gas swirling around the event horizon, the point of no return beyond which nothing, not even light, can escape. The Milky Way is surrounded by a spherical halo of old stars, globular clusters, and mysterious dark matter. This halo extends far beyond the visible disk of the galaxy, perhaps stretching out to 500,000 light-years or more. Globular clusters are ancient, densely packed groups of stars that orbit the galactic center like satellites, some containing hundreds of thousands of stars bound together by gravity in a sphere that might span only 100 light-years across. These clusters are among the oldest objects in our galaxy, with ages of 10 to 13 billion years, formed not long after the Big Bang itself. Studying them gives us a window into the early universe and the formation of our galaxy. Our galaxy is not uniform in composition. It consists of different populations of stars with distinct characteristics. The disk of the galaxy, where our sun resides, contains younger stars, gas, and dust, with active star formation occurring in the spiral arms. These regions glow with the light of newborn stars and the colorful nebulae where they're born. In contrast, the central bulge and the halo contain older stars with lower concentrations of elements heavier than hydrogen and helium. These metal-poor stars formed earlier in the universe's history, before generations of stars had lived and died, enriching space with heavier elements forged in their cores and scattered through supernova explosions. The spiral arms of the Milky Way are not fixed structures like the blades of a fan. Instead, they are density waves, regions where stars, gas, and dust pile up as they orbit the galaxy at different speeds, like traffic slowing in certain sections of a highway. As material moves through these density waves, it gets compressed, triggering the collapse of gas clouds and the birth of new stars. This is why the spiral arms appear so bright and blue. They're filled with massive, hot, young stars that burn brilliantly but briefly. Our sun likely formed in such a stellar nursery billions of years ago, though it has since drifted away from its birthplace as it continues its endless journey around the galaxy. As you rest, imagine yourself floating above this vast spiral, watching billions of stars wheeling slowly through the darkness, each one a story, each one a world unto itself, all bound together in this ancient dance of gravity and light. The Milky Way did not always look as it does today, nor will it remain this way forever. Our galaxy has a history stretching back nearly to the beginning of time itself. The Milky Way began forming approximately 13.6 billion years ago, less than 200 million years after the Big Bang, when the universe was still in its infancy. In those early cosmic moments, small clumps of matter began to collapse under their own gravity, forming the first proto-galaxies. Over billions of years, these smaller structures merged and grew, accumulating more stars, gas, and dark matter, eventually becoming the majestic spiral we know today. Let your breathing slow as we explore the invisible framework that holds our galaxy together. The visible stars, planets, gas, and dust that we can see or detect make up only a small fraction of the Milky Way's total mass, perhaps only 10 to 15%. The rest, about 85 to 90%, consists of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. We know dark matter exists only through its gravitational effects on visible matter. It forms a vast halo around our galaxy, providing the gravitational scaffolding that holds the Milky Way together and influences how stars orbit the galactic center. Without dark matter's gravitational pull, the outer stars in our galaxy would be moving too fast and would fly off into intergalactic space. The true nature of dark matter remains one of the greatest unsolved mysteries in modern physics. Between the stars lies the interstellar medium, the gas and dust that fills the space within our galaxy. Far from being empty, the Milky Way contains vast clouds of hydrogen gas, some cold and dark, others heated to millions of degrees. by exploding stars and stellar winds. These clouds can be enormous, stretching for hundreds of light years, containing enough material to form thousands or even millions of new stars. The dust particles, though tiny, often smaller than the particles in cigarette smoke, are crucial to the story of the galaxy. They're made of elements forged inside stars: carbon, silicon, iron, and other heavy elements. This cosmic dust absorbs and scatters starlight, creating the dark lanes and patches we see threading through the Milky Way's bright band. In the densest regions, dust can completely obscure what lies beyond, hiding entire sections of our galaxy from optical telescopes. The Milky Way is not a peaceful, static place, but a dynamic environment where stars are constantly being born and dying. Star formation occurs primarily in spiral arms, within giant molecular clouds where gas and dust collapse under gravity. Our galaxy creates approximately 1 to 2 new stars every year on average, though this rate has slowed considerably from the galaxy's youth, when star formation was much more vigorous. These stellar nurseries, like the famous Orion Nebula visible to the naked eye, glow with the light of newborn stars, their intense radiation illuminating the surrounding gas in brilliant colors: red from hydrogen, blue and green from oxygen and other elements. Now, let your mind drift to the fate of stars. For every star that is born must eventually die. The most massive stars live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernovae, spectacular events that briefly outshine entire galaxies. These explosions scatter heavy elements into space, enriching the interstellar medium with the building blocks of planets and life. The remnants of these explosions can form neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons on Earth, or even black holes, regions where gravity is so intense that space itself is warped beyond recognition. Our Sun, being a medium-sized star, will have a gentler end, eventually swelling into a red giant in about 5 billion years, engulfing the inner planets before shedding its outer layers and leaving behind a slowly cooling white dwarf. The Milky Way is part of a larger cosmic structure called the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group spans approximately 10 million light-years across, and the Milky Way is one of its 3 largest members, along with the Andromeda Galaxy and the Triangulum Galaxy. Most of the other galaxies in our Local Group are small, dwarf galaxies that orbit the larger ones like moons around a planet. Some of these dwarf galaxies, like the large and small Magellanic Clouds visible from the southern hemisphere, are satellites of the Milky Way, slowly orbiting our galaxy and occasionally having material stripped away by gravitational interactions. Breathe deeply and relax as we contemplate our cosmic neighbor, the Andromeda Galaxy, the largest member of the Local Group. Andromeda, also known as M31, lies approximately 2.5 million light-years from the Milky Way and contains roughly 1 trillion stars, making it significantly more massive than our own galaxy. Despite the vast distance, Andromeda is actually moving toward us at about 250,000 miles per hour. In approximately 4.5 billion years, the Milky Way and Andromeda will collide and merge, though collision is perhaps misleading. The vast distances between stars mean that actual stellar collisions will be extremely rare. Instead, the 2 galaxies will pass through each other, their shapes distorted by gravitational forces, eventually settling into a single, larger elliptical galaxy that astronomers have whimsically nicknamed Milkomeda. Our Sun will likely survive this cosmic merger, though it may be flung to a different part of the new combined galaxy. Throughout its history, the Milky Way has been a cosmic cannibal, growing larger by consuming smaller galaxies. Evidence of these ancient meals can still be found today in streams of stars that wrap around our galaxy. The scattered remnants of dwarf galaxies that wandered too close and were torn apart by the Milky Way's gravity. The most recent significant meal occurred between 8 and 10 billion years ago, when the Milky Way merged with a dwarf galaxy that astronomers call Gaia Enceladus, or the Gaia sausage, because of the elongated orbits of its remnant stars. This collision was so significant that it likely helped heat up the disk of the Milky Way and contributed to the formation of the thick disk population of stars we observe today. Even now, our galaxy is in the process of slowly absorbing the Sagittarius dwarf elliptical galaxy, which has already made several passes through the Milky Way's disk. As you sink deeper into rest, picture this grand tapestry of cosmic time, billions of years of growth and change, of galaxies dancing and merging, of stars being born in brilliant nebulae and dying in spectacular explosions, all part of an ongoing story that stretches from the ancient past into the distant future. The spiral arms of our galaxy have names, each one a distinct region of our cosmic neighborhood. Our solar system resides in what astronomers call the Orion Arm, also known as the Orion Spur or the Orion Cygnus Arm. This is actually a minor arm, a smaller branch that connects two of the major spiral arms, the Perseus Arm and the Sagittarius Arm. The major arms themselves are named after the constellations in which we observe them from Earth: the Scutum Centaurus Arm, the Sagittarius Arm, the Perseus Arm, and the Outer Arm. Each arm is filled with young, hot stars and glowing regions of active star formation, separated by darker regions where fewer stars illuminate the space between. Let yourself relax as we explore the mysterious center of our galaxy, hidden behind thick veils of dust. The galactic core, also called the galactic bulge, is a densely packed region of stars roughly 10,000 light-years across. Here, stars are packed so closely together that if Earth were located near the galactic center, the night sky would be ablaze with thousands of stars brighter than Venus appears to us now. This crowded environment would be a dramatically different experience from our relatively quiet corner of the galaxy. The intense radiation and frequent gravitational interactions near the core make it a far less hospitable place for planetary systems like ours. Scientists estimate that stars near the galactic center are separated by only about 1/10 of a light-year on average, compared to the 4.2 light-years between our Sun and its nearest neighbor, Proxima Centauri. Breathe slowly now and consider the nature of the disk in which our Sun orbits. The Milky Way actually has two distinct disk components, a thin disk and a thick disk. The thin disk, where most star formation occurs, is only about 1,000 light-years thick and contains younger stars, including our Sun, along with gas and dust. These stars orbit in roughly circular paths around the galactic center, all moving in approximately the same plane like cars on a highway. The thick disk extends to about 3,000 light-years above and below the galactic plane, and contains older stars with more random elliptical orbits. These thick disk stars are typically 10 billion years old or more, survivors from an earlier era of our galaxy's history, possibly stirred up by ancient galactic collisions. The Milky Way is permeated by magnetic fields, invisible lines of force that thread through the galaxy like a cosmic web. These magnetic fields, though extremely weak compared to a refrigerator magnet, play crucial roles in shaping the galaxy. They influence how gas clouds collapse to form stars, guide the paths of cosmic rays, high-energy particles that zip through space at nearly the speed of light, and help channel matter, falling toward the central black hole. The magnetic field lines follow the spiral arms and loop high above and below the galactic disk, creating structures that can span thousands of light years. Radio telescopes allow us to map these fields by detecting the polarized radio waves emitted by charged particles spiraling along the magnetic field lines. Now let your thoughts drift to the phenomenon of stellar streams, ghostly rivers of stars that wrap around our galaxy. When dwarf galaxies, or globular clusters, pass too close to the Milky Way, the immense tidal forces stretch them out into long, thin streams of stars that can stretch for hundreds of thousands of light years around the galaxy. One of the most studied is the Sagittarius stream, the slowly unraveling remnant of the Sagittarius dwarf elliptical galaxy, which loops around the Milky Way multiple times, like ribbons around a maypole. These streams are incredibly valuable to astronomers because they act like cosmic seismographs, their shapes and movements revealing the distribution of dark matter in our galaxy's halo. By observing how these stellar streams bend and flow, scientists can map the invisible gravitational landscape of the Milky Way. The Milky Way produces its own form of fireworks through gamma-ray bursts and other high-energy phenomena. In 2010, astronomers discovered two enormous structures extending above and below the galactic center, reaching 25,000 light-years in each direction. These Fermi bubbles, named after the Fermi Gamma-ray Space Telescope that detected them, glow with high-energy gamma rays and appear to be the result of a massive burst of activity from Sagittarius A** that occurred several million years ago. Perhaps our galaxy's central black hole consumed a large amount of matter in a relatively short time, or perhaps it was triggered by intense star formation near the core. These bubbles are evidence that even relatively quiet black holes like ours can have violent episodes that affect the entire galaxy. Let yourself drift deeper as we explore the metallicity of stars, a concept that reveals the chemical history of our galaxy. In astronomy, any element heavier than hydrogen and helium is called a metal, even though this includes elements like oxygen, carbon, and nitrogen that chemists wouldn't classify as metals. The first stars in the universe formed from the primordial hydrogen and helium created in the Big Bang contained virtually no heavy elements. They were metal poor. When these stars died, they scattered newly formed heavy elements into space, enriching the gas from which the next generation of stars would form. Our Sun is a relatively metal-rich star, indicating it formed from material that had already been through several generations of stellar processing. The metals in our bodies, the calcium in our bones, the iron in our blood, the carbon in our cells, were all forged in the cores of ancient stars and scattered through space in supernova explosions billions of years ago. We are, quite literally, made of stardust. The rotation of the Milky Way reveals one of the profound mysteries that led to the discovery of dark matter. When astronomers measured how fast stars orbit at different distances from the galactic center, they found something unexpected. According to the laws of gravity, stars farther from the center should orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But observations showed that stars in the outer regions of the galaxy orbit just as fast as those closer in, maintaining a roughly constant velocity even at the galaxy's edge. This flat rotation curve, as it's called, can only be explained if there's far more mass in the galaxy than we can see. an invisible halo of dark matter extending well beyond the visible disk, providing the extra gravitational pull needed to keep those outer stars moving so fast. As you rest peacefully, imagine the Milky Way not as a static picture, but as a living, evolving system. Stars being born in glowing nebulae, dying in spectacular explosions, chemical elements being forged and scattered, dark matter holding everything together in its invisible embrace, all while the entire magnificent structure slowly rotates through the cosmic night. The plane of the Milky Way, that luminous band we see stretching across our night sky, serves as a celestial reference point for astronomers. The galactic plane, also called the galactic equator, is the imaginary flat surface that runs through the middle of the galaxy's disk. Our solar system is located very close to this plane, only about 65 light-years above it, which is why we see the Milky Way as a band encircling the sky rather than as a distant object. From our perspective, we're looking through the densest concentration of stars, gas, and dust, which is why the Milky Way appears as a luminous river across the heavens. When we look perpendicular to the galactic plane, toward the galactic poles, we can see much farther into intergalactic space, peering out through the relatively sparse halo to observe distant galaxies billions of light-years away. Let your breathing slow as we explore the concept of the galactic habitable zone, the region within our galaxy most conducive to life as we know it. The innermost regions of the galaxy, despite having abundant heavy elements necessary for planet formation, are likely inhospitable to life. Frequent supernova explosions, intense radiation from densely packed stars, and gravitational disturbances from passing stars would make it difficult for stable planetary systems to maintain life over billions of years. The outer edges of the galaxy present a different problem. Stars that are formed from gas with fewer heavy elements, meaning planets might lack the necessary ingredients for life. And the cold, sparse environment provides less energy. Earth sits in what some astronomers call the Goldilocks zone of the galaxy, in a relatively quiet neighborhood with enough heavy elements to form rocky planets, but far enough from the galactic center to avoid its hazards. Breathe deeply now and consider the warp in our galaxy's disk, a feature discovered only in recent decades. The Milky Way's disk is not perfectly flat, but instead has a subtle S-shaped warp, with the edges curling up on one side and down on the other, like the brim of a twisted hat. This warp becomes more pronounced at the galaxy's outer edges, where the disk can deviate from true flatness by as much as 15,000 light-years. The exact cause of this warping remains debated, but it likely results from gravitational interactions with satellite galaxies, particularly the large and small Magellanic Clouds, whose gravity tugs on the outer disk as they orbit the Milky Way. The warp also precesses, or rotates, around the galaxy over millions of years, creating a complex three-dimensional structure. The stellar halo that surrounds our galaxy contains some of the most ancient stars in the universe, cosmic time capsules from the galaxy's youth. These halo stars, many found in globular clusters, but others traveling alone on vast, elliptical orbits, are metal-poor population. Two stars formed when the universe was young and had not yet been enriched with heavy elements from dying stars. By studying these ancient stars, astronomers can peer back through cosmic history, learning about the conditions that existed when our galaxy was first assembling itself from smaller protogalactic fragments. Some halo stars are so old, approaching 13 billion years in age, that they must have formed within the first billion years after the Big Bang, making them nearly as old as the universe itself. Now let your mind drift to the wonder of exoplanets, planets orbiting other stars in our galaxy. For most of human history, we could only speculate about whether other stars had planets. In 1992, astronomers confirmed the first exoplanets orbiting a pulsar, and in 1995, they discovered the first planet orbiting a sun-like star. Since then, we've found thousands of exoplanets throughout the Milky Way, with current estimates suggesting there are more planets than stars in our galaxy. Perhaps 100 to 400 billion worlds, or even more. These planets come in astonishing variety. Gas giants larger than Jupiter orbiting closer to their stars than Mercury orbits our sun. Rocky super-Earths, several times our planet's mass. Water worlds covered entirely by deep oceans. And perhaps, somewhere among those countless worlds, planets where life has emerged and evolved. The famous Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding of planetary systems in the Milky Way. By staring at a single patch of sky containing about 150,000 stars, Kepler detected thousands of exoplanets by observing the tiny dimming that occurs when a planet passes in front of its star. Kepler's discoveries revealed that small, rocky planets are extremely common in our galaxy, and that many stars have planets orbiting in their habitable zones, the region where temperatures allow liquid water to exist on a planet's surface. Statistical analysis of Kepler's data suggests that roughly 20 to 50% of sun-like stars may host Earth-sized planets in their habitable zones. If true, this means there could be tens of billions of potentially habitable worlds in the Milky Way alone. Let yourself sink deeper into relaxation as we contemplate the chemical enrichment of our galaxy over cosmic time. When the Milky Way first formed, it was composed almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. The first generation of stars, massive and short-lived, forge heavier elements in their cores through nuclear fusion. Carbon, oxygen, nitrogen, silicon, and iron, and then scattered these elements into space when they exploded as supernovae. Each subsequent generation of stars formed from gas that was slightly more enriched with heavy elements, gradually building up the cosmic inventory of metals over billions of years. This process of chemical enrichment continues today, with each supernova adding to the galaxy's store of heavy elements. The story of the Milky Way is therefore also the story of how the universe created the elements necessary for planets like Earth and life like us. The Milky Way emits radiation across the entire electromagnetic spectrum, from low-energy radio waves to high-energy gamma rays. In radio wavelengths, we can observe the cold hydrogen gas that pervades the galaxy, mapping its distribution and movement. In infrared light, we can peer through dust clouds that block visible light, revealing hidden star-forming regions and seeing into the crowded galactic center. In visible light, we see the familiar stars that populate our night sky. In ultraviolet, we observe the hottest, most massive stars and the energetic environments around them. In X-rays, we detect the remnants of exploded stars, matter swirling around black holes, and million-degree gas heated by stellar winds and supernovae. And in gamma rays, we see the most violent and energetic phenomena: supernova remnants, pulsars, and the mysterious Fermi bubbles. Each wavelength reveals a different aspect of our galaxy, like viewing a city through different filters, at night showing its lights, in infrared showing its heat, in X-rays showing its hidden infrastructure. As you rest, picture the Milky Way as a cosmic symphony playing across all these wavelengths, each frequency telling its own story, combining to create a complete portrait of our galactic home, a place of endless complexity and beauty floating through the vast darkness of space. The center of our galaxy pulses with an extraordinary phenomenon known as the galactic fountain, a vast circulation of gas that cycles between the disk and the halo. Hot gas, heated by supernova explosions and intense stellar winds, rises thousands of light years above the galactic plane, forming enormous bubbles and fountains of material. As this hot gas rises and cools, it eventually condenses and falls back down onto the disk like rain, enriching it with the heavy elements forged in stars. This fountain cycle takes millions of years to complete and plays a crucial role in regulating star formation throughout the galaxy. Without this recycling mechanism, the Milky Way would have exhausted its gas supply and stopped forming new stars billions of years ago. Let yourself relax as we explore the concept of stellar populations and how they tell the story of the galaxy's evolution. Astronomers classify stars into different populations based on their age, chemical composition, and orbital characteristics. Population 1 stars, like our Sun, are relatively young, metal-rich stars found in the galactic disk, born from gas that had already been enriched by previous generations of stars. Population 2 stars are older, metal-poor stars found in the halo and globular clusters, formed when the galaxy was young. Some astronomers also speak of a hypothetical population 3, the very first stars in the universe, formed from purely primordial hydrogen and helium with no heavy elements at all. These massive first stars would have been short-lived, exploding as supernovae after just a few million years, and none are believed to have survived to the present day, though astronomers continue searching for them in the most distant reaches of the observable universe. Breathe slowly now and consider the remarkable precision with which we've mapped our galaxy despite our location within it. For most of human history, we didn't even know we lived in a galaxy, let alone what it looked like. The breakthrough came in the early 20th century when astronomer Harlow Shapley studied globular clusters and realized they formed a roughly spherical distribution centered far from Earth, revealing that our solar system was not at the center of the Milky Way. Later, other astronomers determined the spiral structure by mapping young stars and hydrogen gas clouds. Today, we use multiple techniques to map the galaxy, measuring distances to stars using parallax and other methods, tracking the movements of gas clouds using radio telescopes, observing how light from distant stars is absorbed by interstellar dust, and using infrared observations to peer through obscuring material. The European Space Agency's Gaia mission has been particularly revolutionary, precisely measuring the positions and movements of over 1 billion stars, creating the most detailed three-dimensional map of our galaxy ever produced. The Milky Way experiences cosmic weather, with vast clouds of gas moving through the interstellar medium like storm systems in Earth's atmosphere. High-velocity clouds are enormous clouds of neutral hydrogen gas, some containing millions of solar masses of material, that travel through the galactic halo at speeds that set them apart from the normal rotation of the galaxy. Some of these clouds may be ancient gas falling into the galaxy for the first time, pristine material left over from the galaxy's formation. Others might be gas blown out of the disk by supernova explosions and stellar winds, now returning in this cosmic fountain cycle. When these clouds collide with the galactic disk, they can trigger bursts of star formation, compressing the disk gas and causing it to collapse into new stars. One of the largest, the Smith Cloud, contains enough gas to form 1 million stars and is on a collision course with the Milky Way's disk, expected to impact in about 30 million years. Now let your thoughts drift to the pulsars scattered throughout our galaxy. cosmic lighthouses that demonstrate nature's most extreme physics. Pulsars are rapidly rotating neutron stars, the collapsed cores of massive stars left behind after supernova explosions. These objects pack more mass than the Sun into a sphere only about 12 miles across, making them so dense that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. As they spin, sometimes hundreds of times per second, they emit beams of radio waves from their magnetic poles. When these beams sweep past Earth like a lighthouse beam, we detect regular pulses, hence the name. The Milky Way contains an estimated 100 million neutron stars, though we've only detected a few thousand as pulsars, because their beams must happen to point toward Earth for us to see them. The most rapidly spinning pulsar known in our galaxy rotates 716 times per second, completing a rotation in just 1.4 milliseconds. The concept of the galactic year gives us a humbling perspective on cosmic time scales. As we mentioned earlier, our solar system takes about 225 to 250 million years to complete one orbit around the Milky Way. In this framework, we can describe Earth's history in galactic years. Earth formed about 20 galactic years ago. Complex multicellular life emerged only about 2.5 galactic years ago, and the dinosaurs went extinct less than 1/3 of a galactic year ago. All of recorded human history, from the first cities to the present day, has occurred in less than 1/30th of a galactic year. Our entire species, Homo sapiens, has existed for only about 1,000th of a galactic year. This perspective reminds us how fleeting our presence has been in the vast story of the galaxy. Let yourself sink deeper as we explore the Milky Way's stellar nurseries, regions where new stars are being born right now. The most famous is the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, located about 1,350 light-years from Earth. This glowing cloud of gas and dust spans about 24 light-years across and contains enough material to form thousands of stars. Within it, the famous trapezium, a cluster of young, hot stars, illuminates the surrounding nebula, their intense ultraviolet radiation causing the hydrogen gas to glow with the distinctive red color. But Orion is just one of many stellar nurseries in our galaxy. The Eagle Nebula, made famous by the Hubble Space Telescope's Pillars of Creation image, shows towering columns of gas and dust where stars are forming. The Carina Nebula in the southern sky is one of the largest star-forming regions in our galaxy, spanning over 300 light-years and containing some of the most massive and luminous stars known. The Milky Way's oldest stars preserve information about the conditions in the early universe, acting as archaeological artifacts from cosmic history. By analyzing the chemical composition of ancient metal-poor stars, astronomers can learn about the first supernovae that enriched the universe with heavy elements. These ancient stars contain clues about the initial mass function, the distribution of masses in the first generations of stars, and help us understand how galaxy formation proceeded in the early universe. Some of these ancient stars show unusual chemical signatures, with unexpected ratios of different elements, suggesting they were enriched by rare types of supernovae or even by exotic events like colliding neutron stars. Each ancient star is like a time capsule, carrying within its composition a record of the chemical environment in which it formed billions of years ago, allowing us to reconstruct the story of how the Milky Way built up its inventory of elements over cosmic time. As your breathing becomes slower and more peaceful, imagine the Milky Way as a vast cosmic ecosystem, with matter cycling through different forms, from diffuse gas to stars to heavy elements and back to gas again, in an endless dance of creation and destruction that has continued for nearly 14 billion years. The Milky Way harbors thousands of stellar remnants called white dwarfs, the slowly cooling embers of stars that once burned bright. When stars like our Sun exhaust their nuclear fuel, they shed their outer layers into space, creating beautiful planetary nebulae, while their cores collapse into white dwarfs, objects about the size of Earth, but containing roughly half the mass of the Sun. With no internal energy source, white dwarfs simply radiate away their stored heat over billions of years, gradually cooling from white-hot to red to eventually, in the far future, becoming black dwarfs, cold, dark spheres of crystallized carbon and oxygen floating through space. The universe is not yet old enough for any black dwarfs to exist. Even the oldest white dwarfs are still faintly glowing. Our own Sun will become a white dwarf in about 7 to 8 billion years, long after it has expanded into a red giant and consumed the inner planets. Let your mind drift now to the cosmic rays that constantly bombard our galaxy, high-energy particles that zip through space at nearly the speed of light. These particles, mostly protons, but also atomic nuclei of heavier elements and even electrons, originate from various sources throughout the Milky Way. Supernova remnants are believed to be the primary accelerators, with the expanding shock waves from stellar explosions flinging particles to tremendous energies. The most energetic cosmic rays carry as much energy as a well-thrown baseball, yet concentrated in a single subatomic particle. As these particles travel through the galaxy, they're deflected by magnetic fields, bouncing through space like pinballs, which means they arrive at Earth from all directions rather than pointing back to their sources. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that rain down on the surface, with millions passing through your body every day, usually without any effect. Breathe deeply and relax as we explore the mysterious dark energy that's pulling the universe apart, affecting even our galaxy's ultimate fate. While dark matter holds galaxies together through gravity, dark energy is causing the expansion of space itself to accelerate. Discovered in the late 1990s through observations of distant exploding stars, dark energy makes up approximately 68% of all the energy in the universe. Within the Milky Way and the local group, gravity is strong enough to overcome dark energy's influence, keeping our galaxy and its neighbors bound together. However, most other galaxies are already receding from us at ever-increasing speeds as the space between galaxy clusters expands. In the far future, hundreds of billions of years from now, dark energy will have pushed most galaxies beyond our cosmic horizon, making them forever unreachable and eventually invisible to any observers in the Milky Way. The Milky Way contains mysterious invisible structures detected only through their gravitational effects on passing light. Gravitational microlensing occurs when a massive object, a star, brown dwarf, or even a planet, passes between us and a more distant star. The gravity of the foreground object bends space, acting like a lens that briefly magnifies the light of the background star, causing it to brighten temporarily before returning to normal. By monitoring millions of stars for these brief brightening events, astronomers have detected countless otherwise invisible objects drifting through our galaxy, including free-floating planets that were ejected from their solar systems, orphaned worlds wandering alone through the darkness between stars. These observations suggest there may be billions of rogue planets in the Milky Way, possibly outnumbering stars. Now let your thoughts settle on the globular clusters, that orbit our galaxy like ancient satellites. We've mentioned these before, but they deserve deeper contemplation. The Milky Way hosts about 150 known globular clusters, though more likely exist, hidden behind the dust and stars of the galactic plane. The largest and brightest, Omega Centauri, contains an estimated 10 million stars and may actually be the stripped core of a dwarf galaxy that the Milky Way consumed long ago. These clusters orbit the galaxy on huge, elliptical paths that carry them through the halo, sometimes plunging through the galactic disk. Each passage through the dense disk can strip away some of a cluster's outer stars, slowly eroding it over billions of years. Despite this, globular clusters are remarkably stable, held together by the collective gravity of their densely packed stars, with some having remained essentially unchanged for over 12 billion years. Let yourself drift deeper into relaxation as we contemplate the sounds of the galaxy. Or rather, what sounds would be like if space could transmit them. Sound requires a medium to travel through: air, water, or solid material, and space is far too empty to carry sound waves as we know them. However, astronomers have translated various astronomical data into sound through a process called sonification. The radio waves emitted by pulsars create regular rhythmic pulses when converted to audio, like cosmic heartbeats. The oscillations of stars can be transformed into ethereal tones, with different stellar vibrations producing different pitches, allowing astronomers to study stellar interiors through astroseismology, much like geologists study Earth's interior through seismic waves. Even the cosmic microwave background radiation from the Big Bang has been sonified, producing a deep hum that represents the echo of creation itself. While the Milky Way is silent to our ears, in another sense, it's full of rhythms and vibrations waiting to be heard. The chemical composition of the Milky Way varies with location, creating what astronomers call abundance gradients. Stars in the inner galaxy, closer to the center where star formation has been more vigorous and prolonged, tend to be more metal-rich than stars in the outer regions, where fewer generations of stars have lived and died. This metallicity gradient provides evidence for how the galaxy formed and evolved, suggesting that the inner regions have been more actively recycling gas through stars for a longer time. Our sun's location, with its moderate metallicity, may be significant for the development of life. Too metal poor, and there might not be enough heavy elements to form large rocky planets like Earth. Too metal-rich and planetary systems might form too many massive planets whose migrations could disrupt the orbits of smaller, potentially habitable worlds. Once again, we find ourselves in a cosmic middle ground. The Milky Way participates in the large-scale structure of the universe, part of a cosmic web of galaxies stretching across billions of light years. The local group, containing the Milky Way and its neighbors, is itself part of a larger structure called the Virgo supercluster, which contains thousands of galaxies and spans about 110 million light years. But even this isn't the largest structure. The Virgo supercluster is just one lobe of an even more enormous structure called Laniakea, Hawaiian for immense heaven, which contains about 100,000 large galaxies and spans 520 million light years. These superclusters are separated by vast voids, regions of space with very few galaxies, creating a foam-like structure often compared to soap bubbles or a cosmic web. The Milky Way is being slowly pulled through space toward the center of the Virgo cluster by gravity, moving at about 400 miles per second relative to the cosmic microwave background. Though this journey will take billions of years, as you rest in deep tranquility, Picture the Milky Way as part of this vast cosmic web, a single thread in the tapestry of the universe, connected through invisible bonds of gravity to structures spanning hundreds of millions of light years, all of it expanding, evolving, transforming,